Hey guys, today we're going to be talking about Lesson 10, Conservation of Energy. This is part of our school closure unit, Momentum and Collisions. All right, so in our previous two lessons on potential and kinetic energy, we've used the example of a roller coaster quite a few times. Right, we know that as the roller coaster is going up, its potential energy is increasing, right, because gravity is pulling down on it. Right, the higher and higher it gets, the more potential energy it has. Right as it gets to that very top peak, right, and it stops, it actually has a ton of potential energy, even though it's not moving for that split second. Once it kind of gets over that peak, right, it starts increasing its velocity faster and faster and faster, right? It's losing potential energy, but that potential energy is converting into kinetic energy, which is the energy of motion. Uh, so, one thing we're seeing this energy transformation: potential, kinetic, potential, kinetic, potential, kinetic, etc. One thing you have to keep in mind, though, is that throughout the entire roller coaster ride, the total amount of energy in the roller coaster never changes. It stays the same. And that's what we're going to talk about in today's lesson. We're talking about the conservation of energy. All right, so just to kind of go a little more with this concept of energy transformations within a roller coaster, there is a little simulation here that I suggest playing around with first before you get into the lesson, just because it kind of gives you more of a interactive way to understand what it is that we're talking about. So I'll let you guys kind of do that on your own. All right, so this is what I'm talking about, right? As the roller coaster moves and goes faster and faster, kinetic energy increases. As it gets higher and higher, potential energy increases. Again, that potential then transforms to kinetic. That kinetic transforms to potential, and when it gets higher, etc. But throughout, no matter where we're at with the amount of kinetic energy we have or the amount of potential energy we have, the total amount of energy stays the same. Now, when we're talking about the law of conservation of energy, we're specifically talking about a closed system, right? Within this roller coaster, we're not adding in any extra energy. We're not pulling out any energy at any point, right? Um, some of you guys know, like if you have Hot Wheels, if you were one of those kids that just had like every single Hot Wheels part, at some points in the track, you could have like these little like spinning motors that would like shoot your car to go faster. It was kind of like a speed boost. Um, at roller coasters, you really don't have that, right? Whatever energy you have is just coming from that potential energy at the beginning, which then converts into kinetic, which then converts into potential, converts into kinetic, converts into potential over and over and over again. All right, the total amount of energy within that system is constant; it stays the same. Right? Another way to kind of express the law of conservation of energy, and this quote or this concept is probably familiar, is this idea that energy can never be created or destroyed; it just transforms. Right? You think about when you turn your light switch on, you're taking electrical energy and that's converting into light and radiant energy, right? So, or radiant and thermal energy, right? Radiant, as in it's creating light. Thermal, right? Some light bulbs, if they're not very efficient, will feel hot. Again, you think about where that energy came from. That energy came from, a power plant that's creating the electricity, and it's creating that electricity by burning a fossil fuel, right? Which is creating heat and steam, which is powering a turbine. If you're in the state of Washington, right, a lot of our power comes from hydroelectric energy, which is where you have the kinetic energy of a river or going through a dam, right? And it's turning these turbines, which is generating electricity. So again, all energy we have is just transforming from one type to another to another to another. Never created, never destroyed. All right. So again, this law of conservation of energy only works within closed systems, right? We're talking about systems where we're not adding energy, we're not taking away energy. So, for example, in this little GIF here, you see this guy holds this little ball, a pretty heavy ball. He releases it, And he is confident enough in the law of physics that that ball won't come back and smash him in the face, because in order to do so, it would need added energy. But he's not adding any extra energy into the system, so he can be pretty confident that it's not going to hit him. All right, we're talking about the law of conservation of energy. We want to figure out, right, what is happening to the total amount of energy in the system over time. Right, if we're looking at a roller coaster example, we want to know how much energy is there at the beginning, how much energy is there after 5 seconds, etc. Right, we know potential and kinetic energy are changing all throughout the ride, but what's happening to the total amount of energy? We can see that the total amount of energy really stays the same throughout. Right, at 0 seconds, right, we have 100% potential energy. At 3 seconds, maybe it's 100% kinetic energy. At 5 seconds, maybe it's a mix of both potential and kinetic. But the total energy always stays the same. Right, so we end up with a horizontal pattern. Right, this total energy doesn't change at all, no matter where we're at in the system. So however much energy we had at the beginning of the ride is going to be the same total energy we have at the end of the ride. Now again, this works for all types of energy, not just potential and kinetic, right? We can talk about elastic energy as well, right? We can talk about chemical energy. We can talk about electrical energy, what have you. It doesn't matter. All our types of energy combined equal the total amount of energy, and that total will not change throughout our entire system. All right, so this is just kind of a summary of that. So again, total energy system does not change. Again, with a roller coaster, no matter what point we're at, the total amount of energy is going to be the same, right? At the top of it, it's going to be 100% potential energy, 0% kinetic. Let's say the total energy there is 50, right? When the roller coaster is halfway down, let's say it's now half potential, half kinetic. So if the total energy was 50, then that's 25 joules of potential energy, 25 joules of kinetic energy, right? When it gets to the bottom, it's 100% kinetic, 0% potential energy. So that is 0 joules of potential energy, 50 joules of kinetic energy, right? All we're doing is we're just adding up our potential energy, our kinetic energy, and by adding them up, they should always equal the same number. So as potential energy and kinetic energy change, their addition, their combination will always equal the same number. Right? Total energy does not change. Time does not matter, making total energy of a system a horizontal pattern. All right, let's go through a little example just to kind of see how this works in reality. All right, so let's say we have a 10 kilogram box that's held at a height of 10 meters above the ground. So we want to find two things. One, what is the box's initial potential energy? And then two, if we drop the box, what is its kinetic energy in the split second right before it hits the ground? So two questions we're trying to answer. And we'll go through this step by step. Now, for all these questions, I always suggest visualize or sketch out the problem if there's not already a visual for you. Right. So, all right, we said we have a 10 kilogram box. It's 10 meters off the ground. So the first question is trying to figure out how much potential energy does it have, right? We know it's not moving. We're just trying to figure out how much energy does it have before it starts to fall. We want to use our formula, right? We learned our potential energy lesson 8, that the potential energy formula is mass times gravity times height. And we want to plug in our numbers. We know that mass is 10 kilograms. We're given that. We know that gravity on Earth is always going to be 9.8. Remember, we learned that in our lesson 8. Height, in this case, is 10 meters. So by plugging in our numbers, we get 10 times 9.8 times 10. Calculate those all together, and you're going to get potential energy equals 980 joules. So we solved question 1. Now, our second piece of this equation is figuring out how much kinetic energy is there right before it hits the ground. Now, before we try to do any math or use the kinetic energy formula, we just need to figure this out more conceptually, right? So we know that at the beginning of the system, before the box is moving, it has 980 joules of potential energy, right? So let's think about what we learned with the law of conservation of energy. We know that at the very beginning, it has 980 joules of potential energy, and it's not moving, which means that its kinetic energy is 0. We know that total amount of energy at any point in the system is going to be potential energy plus kinetic energy. We just found that the potential energy at the top is 980 and the kinetic energy at the top is 0. So we add those two numbers together, 980 joules of potential plus 0 joules of kinetic equals 980 joules of total energy. So the total energy of the system is 980, which means that no matter where the box is in its fall, where it's at the top, 3/4 of the way down, halfway down, all the way at the bottom, right, we're going to have a total of 980 joules of energy. All right, so we know that the total amount of energy is 980 joules, no matter what the height of the box is. So, first piece to figuring out kinetic energy right before it hits the ground is going to be figuring out how much potential energy is there going to be, like right before it hits the ground. So again, let's just use our potential energy formula. Potential energy equals mass times gravity times height. We already know that the mass is 10, doesn't change. Gravity doesn't change, 9.8. In this case, the height is essentially 0, right? So we get, plugging in our numbers, 10 times 9.8 times 0 equals 0 joules of potential energy. All right. So we got our box right at the ground. We know that the total amount of energy is 980 joules, and the total amount of energy is going to be however much potential you have plus however much kinetic you have. We want to plug in our numbers for potential energy when height is 0, which we already did. Our energy total is going to be 980, and that equals 0, right, for potential energy plus kinetic energy. All right, so just do a little bit of basic algebra, and we can figure out that when the height of the box is 0 meters, the kinetic energy is 980 joules right before it hits the ground. All right, so that's our answer to question 2. Right, right before it hits the ground, our box will have 980 joules of energy. Right, so 0 potential, 100% kinetic, which is going to be 980. Right, which is the opposite of our first question, where we had 100% potential, 0% kinetic. Right, they just kind of switched. One thing, just kind of clarify, reason why I say right before it hits the ground is obviously once our box does actually hit the ground and have a collision, right? We're talking about momentum and collisions. The ground is absorbing a lot of that energy, right? So that energy is being transferred into the ground. So we do lose energy to the ground when there is that collision. So that's why we're talking about right before it hits the ground. All right, in here is just a short little video of something that's called Newton's cradle. Some of you guys have seen these before or maybe seen videos of them. If not, here you go. Again, with this particular device, again, it's just an example of two things. One, the law of conservation of momentum, which we've talked about in our first few lessons. Also as an example of the law of conservation of energy. So a couple things you guys will want to look at, right? He goes through a few different tricks, a few different examples. You want to figure out how is this video or this device an example of the law of conservation of momentum, and how is this device an example of the law of conservation of energy. Also, I'm not sure if at any point he just kind of lets them go for the remainder of the video, But obviously, if you guys have played with these before, you know that they do keep going back and forth. But if you come back the next day, it would have stopped, right? So why don't these balls continue to move on for forever? Okay. In summary, in a closed system, energy may change forms, right? Potential may turn to kinetic, may turn to potential, etc. But the total amount of energy is constant. Energy in a system always follows a horizontal pattern. The total amount of energy is all forms of energy added together, right? So if in your system you have elastic energy, potential, kinetic, etc., right? All those types of energy added together is going to be your total amount of energy. We're talking about a system where there's some sort of change, right? The total amount of energy before that change happens is going to equal the total amount of energy after, right? If we're thinking about a car collision, right? However much energy a car has before it collides with another car is going to be the same amount of energy after that collision, right? Just like with momentum, right? It's all conserved. So that's really it for this lesson. It's a pretty short one. In our next lesson, we're going to be doing a little interactive activity. So go ahead and answer the quiz questions below. And then if you have questions, email me, and I will talk to you guys next time.